So this video is about something called arithmetic sequences. And so a sequence is just a list of numbers, and they're in order. So each of those numbers is called a term. So in this particular sequence, 3 is our first term, 5 is our second term, 7 is our third term, and it keeps going, little ... shows that. Usually there's some sort of pattern, but there doesn't have to be. In this particular pattern, you may notice that we're adding by 2 each time. You can make a table out of this. So like the term number, and then the output would be the term itself. For example, term number 1 is 3, term number 2 is 5, and term number 3 is 7, and this continues on. This is actually a function. You've got an input, the term number, and an output, the term itself. If we wanted to make a function for it, we could write like f of x. We could say like, if I put in 1, I get the term 3, and if I put in 2, I get the term 5, and so on. But typically when we talk about sequences like this, instead of f of x, we use the notation a in. It's a little n. It literally means the same thing as f of x. It's just instead of f, we use a, and instead of an x for the input, we use n, which stands for number, just which term number is it. For example, a1 would be 3. This is a1, our first term. This is a2, our second term. This is a3, our third term. And if I say an, that just stands for any term in the sequence. So again, it is a function. And you may notice the pattern here is we're adding 2 each time. If we continue to add 2 over and over again, really we're taking the term number and multiplying it by 2 in some way. And so this ends up being a linear function. Go ahead and take a look at these patterns here, these sequences. We've got a list of terms. In this one, you may notice we're adding 2 each time. And this one, we're subtracting 5 each time. And on this one, we're adding 0.5. And so what did all these patterns have in common? They have in common the fact that you're adding the same number each time. Technically, subtraction is like adding a negative, so it is still addition. So if you ever have a sequence like this, we call it arithmetic. It looks like the word arithmetic, pronounced arithmetic. An arithmetic sequence is just like all 3 of these. It's when you add or subtract the same number over and over again. That number that you add over and over is what we call the common difference. The reason for that is because if you were to take a term and subtract the one before it, you would get that number. That's why we call it a difference, because you subtract the term before it. And it's common because they all have it in common. They all share that same common difference. So usually we use the letter D to represent the common difference. And so in this scenario that we've been looking at, since we're adding 2 each time, we'll call D 2. In class we did this problem about like hexagon trains, and in this case this is also an arithmetic sequence since we were adding 4 each time. In this case the common difference, D, is 4. Go ahead and pause the video and try these. So is this first sequence arithmetic? Well, we add 3 and then we add 3 again, so it's looking good, but then we add 4. So no, it's not arithmetic because we didn't add the same number each time. This one is a cool sequence. You may notice that we're multiplying by 2 each time. While that is a cool sequence, it's not arithmetic. Because to be arithmetic, you have to be adding or subtracting a number each time. This one is multiplying. This is what we call a geometric sequence, and we'll get to that in a later unit. So this is no, it's not arithmetic. This is also a cool sequence. You add 1, then you add 2, then you add 3, then you add 4. This is a cool pattern you may have learned about, where if you take 2 terms and add them, you get the next term in the sequence. It's a cool pattern, but it is not arithmetic, because we're adding something each time, but it's not the same thing. You have to be adding the exact same number each time. This would be an arithmetic sequence if we went like one more step up, but no. This one's kind of all over the place. You add 2, subtract 4, and add 8, so that one's definitely not arithmetic. This one though is, because you subtract 4, you subtract 4 again, subtract 4 again. So yes, it is arithmetic, and the common difference is -4 because it's going down by 4 each time. So it would be helpful when we have these sequences to come up with an equation to represent the sequence. Because, for example, let's say I wanted to know like the 100th term in the sequence. I personally don't want to sit here and write out 100 terms, but if I had an equation, I could just plug in 100 and it would spit out the 100th term. So that's kind of going to be our goal for the next few examples here. So how can I describe this particular sequence with a formula or a function? It starts with 7, and then notice that we're adding 2 each time. So the common difference is 2. It is an arithmetic sequence. All right, so go ahead and think about that for a second. One way that you might come up with a formula for this is take the first number, 7, and that's basically my first term. So like the first term is 7, and then after that, what happens? For the next term, each new term, we take the previous term and add 2. This may not look like a formula that you're used to, but it works. We start with 7, and then for each new term, you take the term before it and add 2. Doesn't really look like, again, something you might be used to, but this is something called a recursive formula. A recursive formula is built on whatever comes before it. Like when something recurs, it like repeats over and over. So this is called a recursive formula. You have this on your formula sheet, and it looks like this. So arithmetic sequence formulas, and then it gives you the recursive formula. And this looks a little different than what I just wrote, but it's actually the same thing. It says for any term, an, you take the term before it, an minus 1, and add the common difference. For example, if I wanted to find the 4th term, a4, I would do a4 minus 1, which is really just 3. So if I take the term minus 1, that's going to give me a3, which is the term before it. And then I add the common difference. Or if I wanted to find a100, the 100th term, I would take the 99th term and add the common difference. The problem with this is you have to know the term before it. So let me see here. So let's go back to this one real quick. To write a recursive formula for this one, I could say instead of each new term, I would represent this with just an. And for the previous term, you just do an minus 1 plus 2. You also need a starting point. So like in this case, if I just keep going back, like to find the 100th term, I would use the 99th. To find the 99th term, I would need the 98th, and so on. But eventually I need the first term. And so in addition to this right here, I would also need to say, okay, by the way, the first term was 7, which is kind of what I said right here. This is a recursive formula for this sequence. So let me write that down for you just a little more explicit. To come up with a recursive formula, you need two parts. The first term of the sequence, A1, and that is not on your formula sheet, you're going to need to remember that. And then you need the formula itself. It's the pattern or rule to get to the next term based on the one before it. And that is on your formula sheet. It looks like this once again, and you really just fill in the D, and then you have to write the first term, and that's literally all you have to do. For example, here is a recursive formula for a sequence. It says the first term, A1, is 5. That's the first term in the sequence. And then for the next term, you take the term before it and subtract 3. Basically just keep subtracting 3 each time. So 5 minus 3 is 2, and then -1, and -4, and so on. Just to be explicit about how this works, like say I want the next term, A2, then I would take A2 minus 1, which is just A1, and subtract 3. Well, what is A1? It's the first term right here, 5. So do 5 minus 3, and that's how I got 2. And then to find A3, you'll take A2 and subtract 3. And to find A4, you'll take A3 and subtract 3. So you just keep getting to the next one by taking the term before it, subtracting 3, and moving on. For example, let's try this one. This one tells me the first term in a sequence is -6. The common difference is -4. I want to find the first 3 terms of the sequence and write a recursive formula for it. So, first I need to say, okay, A1 is -6. I know it already gave me that, but we need to start with that information. I guess if I want to write out the first 3 terms, it starts with -6. Then what would the next term be? The next term would be, you're going to do -4. So -6 minus 4 would be -10, and then -4 again would be -14, and so on. Those are the first 3 terms of the sequence. Okay, so to write a recursive formula, again, you start with this, and then for any term after that, you just take the term before it and subtract 4. That's it. All you have to fill in is the D part, really. You can just leave this stuff. This says to find this term, take the term before it, and subtract 4. So this is my recursive formula. That's the first 3 terms of the sequence. Okay, so a recursive formula is nice, but it's not the best because, like, say I want to find the 1000th term. If I try to plug in 1000 for n, I'm going to have to know the 999th term. And to find 999, I would need to know 998, and so on. And you keep having to work backwards. And so I can't jump right to what I want. And so there's a second option for writing a formula for sequences, and it's called an explicit formula. This is also on your formula sheet. It looks like this. And what this allows you to do is, it's literally just a function. And it's explicit because it jumps straight to the point. Like I could plug in 1000 for n, and it would spit out the 1000th term. So explicit formulas are a little more nice in my opinion. You'll need to know both. Okay, just to translate a little bit, an once again stands for the term, and n is the term number. So that's n here. Once again, all you have to fill in is the first term, A1, and the common difference, D. What's happening is A1, let's go back to that hexagon sequence. The hexagon sequence, you started with 6, and then you added 4 each time, basically. But you only added 4 after the first term. And so you start with the first term, and then you add the common difference over and over, but you don't want that difference to be multiplied by n. You only want the difference, say there were 5 terms in the sequence, Say there were 5 terms, you would only want the common difference 4 times. Basically 1 less than however many terms you have. So that's where this n minus 1 is coming from, just if you were curious. Here's an example of an explicit formula. Let's say I want to know the 57th term. Let's go with 10 because it's easier. Let's say I want to know the 10th term, A10. I would just fill in 10 for n, and it would be 50 minus 8, which is 42. So the 10th term is 42. See how explicit formulas are a lot nicer because they're not built on the term before it. So let's go through some examples. Given this explicit formula, find the first 5 terms in the sequence. So to find the first term, just plug in 1. To find the second term, plug in 2, and so on. So A1 equals negative 6 plus 5 times 1. Just put in 1 for n, just like any function. So that's negative 6 plus 5, which is negative 1. That's the first term. A2, we'll plug in 2. Negative 6 plus 5 times 2, which is 10 minus 6, so 4. A3, we'll plug in 3. Which is 15 minus 6, so 9. You're probably starting to see a pattern at this point. A4, we'll do negative 6 plus 5 times 4. 20 minus 6, so 14. Notice that we are just adding 5 each time, which is because of this, 5 times the term number. So if you add 5, add 5, add 5, and so on, that would get me to the 5th term, just add 5. So A5 equals 19, without even having to plug it in. If I want to find the 25th term, again, I'll just plug in 25. So do the formula, negative 6 plus 5 times 25, which is 125 minus 6, so 119. So the 25th term is 119. And this one I want to actually write an explicit formula for this function. So it gives me my first term, negative 6, and the common difference, negative 4. So like this sequence would be negative 6, negative 10, negative 14. We did this in a previous example, but in that case we did a recursive formula. Now we're going to do an explicit formula. All right, so really you can just follow your formula on your formula sheet. It looks like this. So A1 plus n minus 1 times d. The d can go in front or behind, it doesn't matter, and the plus A1 can go in front or behind, it doesn't matter. But so just fill in the first term, which it gives you, negative 6. Leave the n, because the n, you want to be able to plug in any number. For the common difference, it's negative 4. And that's pretty much it. This is an explicit formula. You may want to simplify a bit because I can distribute that negative 4. So that would be negative 6 plus negative 4n and positive 4. And then, so we've got negative 4n, negative 6 plus 4 is negative 2. So that's a slightly simplified version, but either of those are fine. All right, notice that the y-intercept we got is not the first term. That would be like if I backed up to the 0 term, it would be this. Like if I backed up another 4, basically, I would be at negative 2 because the input of 0 would give you this, but that doesn't really make sense in terms of our sequence. Sometimes you might be given a sequence represented visually. For example, this pattern is an arithmetic sequence. So like this first one has 1, 2, 3, 4, 5 squares. So A1 is 5. this one takes those 5 squares and adds another one on the outside. So it adds another 4. So this A2 is 9 squares. A3 is 13 squares. Again, it adds another 4 squares. And so you may notice our common difference is 4 because I'm adding 4 each time. If I want to write a function to represent this pattern, I get to choose. Do I want to use recursive or explicit? I'd go with explicit, but if you want to do recursive, you can. For an explicit formula, I'll take the first term, 5, and then add the common difference n minus 1 times. Again, just as a reminder, that's because I'm not adding 4 the very first time. This is what I start with, then I add 4, and then I add another 4. But at this point, I've only added 4 twice, even though it's the third term. That's why we use n minus 1 in the formula rather than just n. If I want to simplify, I could distribute, so that's 4n minus 4 plus 5, which simplifies to 4n plus 1. So this is a formula I'm going to go with. You don't have to write it in this sequence notation. You could write it as a function. So instead of an, you could say f of x. They mean the same thing. And instead of n, use x. Both of these mean the same thing. So if you see either of these, they're both correct. If I wanted to write a recursive formula for it, I would just say, okay, a1 equals 5, and then for the next term, take the term before it and add 4. So this would be a recursive formula, whereas this is an explicit formula. All right, let's try another one. This one's multiple choice. Which of these expressions can be used to find the nth term in the following sequence? N is the position, and then this is the actual term. So in this case, you're going to need to write an explicit formula for it. Or you could also just test the answer choices. That always works too. Like, if you plug in 2 for n, are you going to get out 9? This one will not work. Here, if you plug in 2, does 6 plus 4 give you 9? Nope. Here, if you plug in 2, do you get 9? Nope. Here, if you plug in 2, do you get 9? Yes, we do. So that's the answer. Let's see how they get there. They get there because they use the explicit formula. You take the first term, 5, and then you add the common difference, which is 4. We're adding 4 each time, times n minus 1. This is actually the same sequence that we just did. You may not have realized it because it was a table rather than a picture, but they started with 5 and then they added 4 each time. So this is the same function that we actually just did, and we get, once you simplify, 4n plus 1, just like we did right here. All right, just a couple more slightly more difficult examples. Everything we've done so far, I gave you the first term, but in this example they don't. You're given the 38th term. It wants you to find the first 3 terms and a recursive formula. To write any formula, you need a1, the first term, and the common difference. We have the common difference, but we need to get back to the first term. So like, if this is the 38th term, and it's negative, hold on, it's A38, and it's negative 53.2, if I go back a term to A37, I would basically need to go back negative 1.1, and then I would go back another 1.1 and another 1.1, and so basically I need to keep backing up how many times? So how many jumps is it going to take to get from A38 all the way over to my first term? Think about that for a second. From 38 to the first term, that would be a total of 37 jumps. because I don't go all the way to 0. Basically, to get to the first term, what you could do is, instead of sitting here and just typing it over and over again, this way we're subtracting 1.1. If I go that way, I'll need to add 1.1 because we're going backwards. Basically, I need to take that 38th term and add 1.1 and add 1.1 again and again and again 37 times because it takes me 37 jumps to get back to A1. And when I do that, don't know what that is. So negative 53.2 plus 1.1 times 37. That gets me negative 12.5. This is A1. If I were to take this and subtract 1.1 and subtract 1.1 and subtract 1.1, eventually I would get that 38th term, negative 53.2. Now that I have the first term, I can answer this problem, which was, first of all, find the first 3 terms. So negative 12.5 is the first term. If I subtract 1.1 from it, that would be negative 13.6, and then negative 14.7, and so on. For a recursive formula, I'll say, all right, A1 was negative 12.5, and then for any term after that, I'll just take the term before it and add the common difference. In this case, subtract 1.1. Remember, this is on your formula sheet. All you got to do is plug in the common difference. So that is my recursive formula. Yeah, let's go with that. Another optional way you could do this one is basically plug it into the explicit formula. So if you didn't like the way we just did it, think about this another way to get back to the first term. So the explicit formula looks like this. A term equals the first term plus n minus 1 times the common difference. We actually have most of this. We have the difference, it's negative 1.1. We're just looking for A1. So another way you could get back to A1 is you could actually fill in this information to the equation. For example, I know that A38 is negative 53.2. I know that when I fill in 38 for n, I get negative 53.2. Basically, fill in 38 and you get out negative 53.2. This is helpful because now I can solve for A1. So this would be 37 times negative 1.1. So 37 times negative 1.1 would be negative 40.7 plus A1 equals this. And then add that to both sides of the equation. And that should be the same thing we got before. Yeah, negative 12.5 equals A1. So that's another way you could get back to the first term, is fill in everything in the explicit formula and it would take you back to A1. You could solve for it. Okay, let's try one more. Maybe 2 more. Okay, on this one, again, we're not given the first term. And we're also not given the common difference. The 14th term is this, the 46th term is this. How much are we adding each time? Basically, you're trying to find the slope between them. So like, from 3055 to 4655, how much has changed? Basically, you can find that by doing 4655 minus 3055 and see how much that is. That would be 4655 minus 3055, 1600. Divide that by how many terms have passed. How many terms has it been from 14 to 46. You can find that by doing 46 minus 14, which is 32. So this is how much has changed divided by how many terms it's been, and that should give you, what is that, 50. Basically, it's the slope. It's the change in y over the change in x. It's the change in the terms versus the change in the term number. And it's 50. So this is the common difference, which is basically like the slope. It's the number you were adding each time. If we added 50, 50, 50, we would get from here to here. All right, now we gotta, again, work back to the first term. You can do it like I just did by plugging everything in and solving for A1, or again, we could think about it as, okay, well, if the 14th term is 30, 55, how many jumps back am I gonna have to make to get to A1? And that would be 13 jumps to go from 14, basically minus 1. So if you take this and you subtract 50 and you subtract 50 again and you subtract 50 again 13 times, that leads you to 2405. Okay, so that's my first term. So my recursive formula is my first term is this, which I just found, and then for any term after it, take the term before and add 50. Okay, just one more. No, this is a long video. In this case, this is the one we did 2 examples ago. It gives me the 38th term. I want to find the explicit formula. Let's go back to where we were. So we already did the work pretty much. We backed up to the first term, which was negative 12.5, and we already knew the common difference was negative 1.1. So to find an explicit formula, I would just do an equals the first term plus n minus 1 times the common difference. I'm just filling that into the formula from the formula sheet. You fill in A1, you fill in the common difference. Leave n because that's part of the formula. We can simplify this a bit by distributing negative 1.1. So that's negative 12.5 minus 1.1n plus 1.1, which is negative 1.1n minus 11.4. And that would be an explicit formula rather than recursive. Let's make sure this works. Let's see if we did this right. If we put in 38, will we actually get out negative 53.2? So negative 1.1 times 38 minus 11.4. Let's see if that worked. So negative 1.1 times 38 minus 11.4. And it does give me negative 53.2, which is good. That's what I